to what's left, we essentially just have chapter 13 to do. And that's going to involve us doing some more hypothesis tests. And today, we're going to look at the hypothesis test of a single mean. A lot of what we've done in hypothesis testing is similar to this one. So let's show you what it would look like. You're going to have a story. So let's suppose my story is this, that I believe that Scotsmen that their average height is greater than or equal to 67 inches. So that's what I would like to see if I can prove. I believe that the average height of Scotsmen is greater than or equal to 67 inches. And we're going to set up an hypothesis test to see whether or not we can prove this. So we're going to have a null hypothesis and we're going to have an alternate hypothesis. Now we're talking about averages here, right? Means, in other words. And the null hypothesis is that it's 67, and the alternate is that it's greater than 67. Now, if I wanted to prove that the average height of Scotsman was less than 70 inches, this would be 70 and this would be less than 70. So whatever these two numbers are, they're always the same. And the null hypothesis, regardless of what this textbook says, is always going to be mu, the population mean, equals that number. And the alternate in this case is greater than. Now, just like we had when we did proportions, isn't there three kinds of hypothesis? There's a right-tailed, there's a left-tailed, and there's a two-tailed. That's still going to be true here. Also, this number 67 is called mu naught. So if you ever see the word or the term mu naught, they mean that guy there, right? So if you imagine a question where they gave you this information and they said, what is the value of mu naught? You will say it's 67. Now, this particular story that I've just given, that I want to prove that the average height of Scotsman is greater than 67, this is a right-tailed test. Are you comfortable about how you know it's a right-tailed test? Can you tell greater than is right? So let's have my second story. And let's suppose we're talking about England. And we believe that the average weight of English males is less than 180 pounds. Now, if I was setting this up as a hypothesis test, I'd have a null hypothesis and I'd have my alternate. And the average, 180. And this fella, less than 180. And in this story, mu naught would be 180. And what name would we give to this hypothesis test? What kind of name like this would we use?
Left-tailed.
Left-tailed. And then for completeness sake, we'll have the third possibility. So we'll pick on the Welsh this time. And we believe that on average, that that Welshmen don't drink 7 units of alcohol, right? It's not 7 units. It could be bigger, it could be less, but it's not 7 units. And in that story, the H naught will be mu equal to 7, and the alternate would be mu not equal to 7. And in this case, the mu naught would be 7. And this would be a two-tailed test. Are we comfortable about the 3 basic stories that you typically get in these hypothesis tests involving means, where you're trying to prove something's bigger than 67, or you're trying to find evidence to prove that it's less than a number like 180, or you're trying to find evidence that it's not equal to something, right? It's different in whatever it might be. Are we comfortable about that setup? That's typically the first thing you do. So let's return back to the Scottish one. Question?
On that, yeah. When I try to enter the
You're breaking up,
exclamation
Robert.
point
Yes.
in WebAssign for not
Yeah, so you would write, exclamation mark equals 7. That's how you would write it. You were saying you were trying that in WebAssign, and what happened?
it wouldn't accept the answer. It said it was ungradable because I wasn't doing it correctly, I guess. But I was putting like P exclamation point and then a number. Should I leave the P out of there or?
No, the P, if you were doing proportions, the P is part of the question, so you need it. You gotta, if it's just a P, it should work fine, but I'd have to see it to have a look at what you've typed, because it may be something less obvious. So let's return
If
back
I
to
run into it,
yes?
again, I'll save it now.
Perfect. Yeah, and that way I can have a look at it. Okay. Well, let's go back to the Scottish one, right? So I believe that the average height of Scotsman is greater than 67 inches. And I've already set up basically the start again. So Scotsman, I believe that their average height, I want to prove that they're greater than 67 inches. That's my goal. I may or may not be able to prove that. And I've set up my null hypothesis, I'm rewriting that. And the alternate is what I'm wanting to prove, in this case, that. So far, so good. Now, there's going to have to be a significance level attached to a hypothesis test. And since this book has no imagination, I think every single one that I've seen, at least, hasn't it always ended up being 5%? Anybody done questions? Isn't it kind of 5%? If they don't tell you who it is, use 5% as well. So what do? Well, I go out and I get a sample. And let's say my sample is 80 people. And I find the average height of them. And it ends up being 69 inches. And we're going to use this sample to try and determine whether we have enough evidence to show that the average is bigger than 67. Would you agree that 69 inches, at least superficially, seems to be working, right? It's bigger than 67, right? 69 is bigger than 67, so that's some kind of evidence. But is it statistically significant? That's a little bit different. Now, let's talk a little bit about when you should be conducting hypothesis testing in the first place. Well, one of the ways you can do it is the population symmetric? I would use the word normal in shape. Actually, I would also use the word bell-shaped because they have different names for the same thing. So does the population look like that? If the answer is you got a sample from a population that looks like this, it's okay to do the hypothesis test, even with small samples. Right? So this is okay. even with small samples. And small could be, you know, only 20 people, right? 2. Suppose population is skewed or just really ugly. You know, like that. That particular one's skewed to the left. But couldn't you have skewed to the right? Couldn't you have double hills? Couldn't you just have randomness, right? If it ain't normal, it belongs in the second category. Now, is this population is skewed in some way? Then your sample
Yes.
needs to be about 30 people. As long as it's about 30, it'll cope with weird data because we're going to use the t-distribution, and the t-distribution is very forgiving. But you still need a fair number of people. Would you agree it wouldn't be a good idea to do it with 5 people, right? No matter what you've got, right? But if the population has got something skewed about it, it's random, it's 2 hills, whatever it is, weird shape, then you really need 30 people. 3, shouldn't the data be unbiased and random? Right, so you don't want to, you know, I don't know. Well, how could you get biased data? You can get biased data the usual way. Couldn't you get it by the people you ask or how you ask it? You know, even if the answer is a number, you know, because typically we're talking about numbers here, right? Not percentage of people who said yes, but how tall are you? How heavy are you? How many coins you got in your pocket? How many kids do you have? You know, questions like that. You could get biased data if you're not careful. And shouldn't the sample be a fair representation of the population? So that would be random, right? If I was interested in the average height of Scotsman, would you agree it wouldn't be a good idea for me to only pick people who happen to play in a basketball team? I mean, would you agree that's a bad sample, right? They're taller than typical, right? Or, you know, some other situation where the people were bad. So as long as this is true, you can pretty much guarantee that the hypothesis test is going to be useful. They don't spend a great deal of time throwing things out, you know, saying, oh, you can't do it. I guess it makes sense. There's not much point in giving you a homework question where you turn around and say, well, there's no point in me doing the hypothesis test on it, because that kind of the question's finished. So we've got the Scottish guys. I got this. Where am I off to next? Well, I'm going to have to find the standard error of a sample. And I forgot to tell you, so I'm now going to tell you that the standard deviation of my sample of 80 is 2 inches. You have met this guy before. You met him when you did confidence intervals. Does anybody remember what the formula for the standard error of the mean is? And it uses some of these numbers here.
Isn't it the standard deviation over the square root of the sample?
Yes. So in this case, it's going to be 2 inches divided by the square root of 80. And so here we go. 2 divided by the square root of 80. And that answer is 0.224, at least the 3 decimal places. So we've set up our null and alternate hypothesis. We're now calculating the standard error. Once we have the standard error, we're going to have, I believe it's typically called the statistic. Now, in different worlds, the statistic has different names. Isn't the statistic called the Z-score when you deal with proportion, but it's going to be called the t-score when we deal with means. And its formula is mu naught, sorry, let's get this right way around, x bar, take away mu naught over the standard error. Now, x bar was 69. Mu naught was 67. Do you see how the mu naught kicks in? And it's going to be divided by 0.224. And at this point, I would just go to my calculator and do 2 divided by 0.224. And I believe, let's try that again. 2 divided by 0.224. And the answer I got is 8.9, which is pretty decent size. T-scores are very like Z-scores, right? They do the same job. A very big T-score is highly unusual. Now, to finish with, we would find the p-value. Almost finished. Second thing from finished. We're doing it by hand. The p-value would be the probability that you got a Z-score greater than 8.9. That guy, you would have to use salt. There's no way of avoiding it, right? So I'm going to, if you give me a few moments, I'm going to show you where to use that. Right, I'm just trying to find any old salt. It doesn't really matter what one I've got, just so we can plug the numbers in. So we get the p-value by finding the probability that we get a t-score greater than 8.9. So here we go. There's my salt button. Right, I'll bring, oh darn it, I've got a window on top of the window I want. There we go. Right, are you looking at salt? Can you see that? Right. Now, in the guy that we want, we are basically going to go t-distribution. Now, in this sample, the data was 80, right? There was 80 in the sample. It's only a little tweak, but you should do it. What degrees of freedom do you have when the data has 80 numbers in it? It's not 80. What number do you use? It's almost 80, but what number do you really use? Degrees of freedom is n take away 1. You just use one less. That's all. So if you have 200 numbers in your data, just use 199. Right. Now we got all of that. Now what do I want? I want a guy greater than 8.9. So greater than is right-tailed. And I want greater than 8.9. And the answer is so small that I think this does 6 decimal places. So to 6 decimal places, the answer is 0, right? It's 0.60, maybe 6 zeros and a 2, right? But it doesn't go that accurate. And that is our t-score. Sorry, our p-value.
Where did you get the 79 again?
80 in the sample size, take 1 away from it, gets you 79. So if your sample has 40 numbers in it, your degrees of freedom will be 39. So we just got a p-value. I know it's at least got 6 zeros in it, might even have some more. But for all intents and purposes, would you agree it's 0? So final step. Is our p-value less than alpha? Have you noticed how similar it is to the other hypothesis test? So is 0 less than 0.005? And that's a definite yes. And so our conclusion is there is enough evidence to reject H naught. Right? And if you reject H naught, isn't that also there is enough evidence to prove that the alternate is true? So haven't we just proved that the average Scotsman is greater than 67 inches tall? And that's pretty much the process. So you're going to have some questions at the end where we use the whole thing is done by Sol. So we won't even need to do any of this. This is all going to be done. For the most part, it's going to be done for us. We'll show you how that happens. And then at the beginning, they've got some early questions where we get to do some of these calculations, like finding the standard error maybe, or finding the t-score, for instance, right? Or set up the null and alternate hypothesis. So I'm not quite sure where I am right now, so I'm going to go back out and in to make sure that we're in the homework. Okay, I got the questions set up here. Let's have a little look at these early ones. These are the, pick the right answer. Might as well just do these together. You know that you could eventually guess them. Now, one of the two possible conclusions in a hypothesis test is to accept the null hypothesis, and that is false. You never accept that the null hypothesis is true, or just accept it. You either say there's not enough evidence to reject it, right? Or you say there is enough evidence to reject it, right? So hypothesis tests can only provide evidence that the alternate is true. It never tells you that the null is true. It seems a bit, what's the analogy to that? If you think of court cases, do you know that when you have a decision made in court, isn't the two answers guilty and not guilty? Guilty is like the alternate hypothesis, right? You did the crime. You are guilty of it. But isn't not guilty not the same thing, if you're being pernickety about it, as you are innocent? Although people come out of jail say, yeah, I've been exonerated, I am innocent. The verdict was not guilty. If you were being really particular, isn't not guilty? We don't know if you've done the crime or not, but there certainly wasn't enough evidence to prove that you did it. Right? Would you agree that there are some people who have committed crimes and got away with it, right? So I want you to think maybe in that context. When you do a hypothesis test, you can say you are guilty. Now, will you get that wrong sometimes? Sure you will. What percentage of the time will you get it wrong? Whatever the p-value was. That's why you want the p-value really, really small, don't you? So that if you get it wrong, you don't get it wrong that often. Now, B, the statement reject the null hypothesis and the other statement accept the alternate are equivalent. Yes. If I say that the null hypothesis has been rejected, in that same sentence, I'm also assuming that the alternate has to be true. Now, explain whether each of the following. Hypothesis and conclusions from a hypothesis testing apply only to the sample. A hypothesis test is talking about what we believe the population value is. The sample is just the evidence we collect to try and prove it. So that's why that's not true. It's the population that we're interested in. The p-value is calculated with the assumption that the null hypothesis is true. Yes, it is. We'll just let you figure that one out. Now, explain why a standardized statistic is used in a hypothesis test. What they're talking about here is, why do we use a t-score? Why don't we just say, well, you think it's bigger than 67 and it was 69 because the difference between those two is 2. Why don't we use just the difference between the hypothesis and the mean? And the main reasons we don't do that is that doesn't take into account of the variation. Would you agree that if you got a 2-inch difference and it was only 20 people you asked, wouldn't that be less significant than if the average was 2 inches and you did it with 1 million people? Can you imagine that the sample size that you got your data from isn't that important in deciding is that difference significant or not? So that's essentially what that's about. And I'll let you do that one. Okay, let's do some question 6. A botanist for a large rose farm is told that the company's current average is $475,000 in sales annually. The company hires her to work as an outside consultant in order to increase their annual sales revenue. So the null hypothesis is that it still stays at 479, right? You spent some money, but you never improved anything. This would be a one-tailed test. Wouldn't the alternate be she did a good job, right? She increased the profits. So how would you check that? I guess at the end of the year, wouldn't you see what your revenue is and say, well, that didn't work out, you know, nothing happened. Okay, a chemist believes that a cornfield must be treated with a fertilizer on average 5 times over the growing season if you want to get optimal growth. However, she is curious about determining if the corn could do equally well with fewer treatments. So the null hypothesis is you leave it as 5. The alternate, less than 5. And that's a one-tailed test. And there's a similar question, so I'll just skip by that one. Here is their 5 steps, similar to the ones that I did. Determine the null and alternate hypothesis. The thing they're calling summarize the data, wouldn't that essentially be calculating the standard error and the t-score? There's your find the p-value, which we would do using SALT. Then you would do, is the p-value less than alpha? And then you would say, okay, what's your conclusion based on what happened in step 4? Can any of the 5 steps be done before collecting the data? Step 1 should be done. Shouldn't you have already set up what your null and alternate is, and also your significance level before you start collecting data? That's what they're getting at there. Many cars have a recommended tire pressure of 33 psis. At a roadside vehicle safety checkpoint, officials randomly selected 50 cars and they got the tire pressure. So the parameter of interest here is the average tire pressure for all tires. And we're interested in, is it 33? So won't the null be 33? And we think that people are not doing, not blowing up the tires sufficiently. So the alternate would be, is there evidence to prove that it's less than 33? So you can imagine that you stopped 50 vehicles and the average came out as 32. Wouldn't that be evidence that people aren't blowing their tires up to 33, for instance? Now, a box of Yvette's favourite cereal states that the contents are 13 ounces. She is suspicious because her package never seems full to her. So she plans to measure the weight of the contents of the next 30 boxes she buys. And let's see what we're interested. The parameter here is the average weight of contents of the population, right? How many, of all the boxes of this cereal, what's the average? The null hypothesis is it's 13, and the alternate is that it's less than 13. And can you imagine she did it and she came up with the answer that the average weight was 12.8? Wouldn't that be evidence that she'd been shortchanged? On the other hand, if it was 13.1 or 12.9, wouldn't that be exactly what you would expect? You know, a little variation because never the same. Unconnected to this, but it kind of makes sense to me because I've had that same feeling. You know, you get a box and it's a huge big box and then you open up and there's that bag inside. Isn't the bag inside at least 2 inches lower than the box it came from? And sometimes isn't the bag got a little bit of air in it? Now, it doesn't mean that they've shortchanged you in weight. Couldn't you be getting exactly what the box says, right? 16 ounces of cornflakes. Don't they make boxes bigger to make you think you're getting a lot of cornflakes? Isn't that basically just psychological? Right? It's not uncommon for manufacturers to make the boxes or the tin or whatever it's contained in larger than the contents that are inside. And that's just because people look at something and say, oh, that's a big box, that's a good deal. And you're buying air and cardboard when you do that. Right, now this question here is asking us to get the t-score. So let me kick that number out because I don't want you to see that now. So we've talked about that kind of, oops, there we go, question before. So let's see what that would look like in real life. Now, if you want to do the t-score, isn't it going to be X bar, so I'll put a little bracket around it, 55, take away mu naught, which in this case is 45, and then won't you divide it by the standard error? How will I get the standard error? Won't I take 70 and divide it by the square root of 121? So this guy here would be S divided by the square root of n, in this case 121. Now I'm going to take that calculation and see what it looks like. So the standard error is 70 divided by the square root of 121, which is 11. So I get 6.34 and some stuff. And so 55 take away 45 divided by 6.364. And the number I get is 1.571. I'll go back up here, put that on. And I want to see that guy. And there you go. Didn't I say 1.571? 1.57. Do you see it work? Right. Can you imagine doing the same thing for this guy? For this guy? Are we comfortable with that, or do you want me to do one more of these? Are you happy about getting a t-score when they tell you all this stuff here? Are we comfortable? Can't tell if you're comfortable. Are we good, or do you want to see a calculation? We're good, okay. So I'm now going to move on. And let's look at finding p-values and t-scores and all that good stuff using SALT. Okay. So in this question, we're being asked to find the p-value. And when it says draw the sketch, can't you just look at your picture that you get in SALT and pick the one that looks like it, right? So in this case, this information here, right, is going to be used to calculate the p-value. So bringing this guy over, here we go. And I'm going to have to do some stuff at the side, and I don't want to do this jumping back and forward. So we know that n is 27, but in this question we're told t is 2.4. So if I go in here, if n is 27, won't the degrees of freedom be 26? And then I want to know the alternate hypothesis is mu greater than 0, mu greater than mu naught. So that means I'm looking for greater than 2.4. And the p-value comes out here. Let's see if I can maybe put them side by side. That might make it a little bit easier for you to see where I'm getting all these numbers from. Okay, are you seeing two side by side things right now? We'll have to go in and out. Can you see two different windows side by side?
Yeah.
We can. Oh, great. Wasn't expecting that. Right, so you can see what's going on here. The null hypothesis is this guy and the alternate is this guy. Do you notice that they didn't even tell you what that number is, but that doesn't mean you can't get the p-value. T distribution, 27 in the sample makes that 26. This is 2.4, right? That's the t value. So we want to find the probability that t is greater than 2.4. And you might say, well, why is it not less than or not equal to? Can you see the alternate uses a greater than? That's why I'm using a greater than. So the fella that we got here is our p-value. And into 4 decimal places, you get that guy. Now it says, draw a sketch of what that looks like. So if you look at this guy, can you see it's basically a bump with the right-hand side shaded? And the one that has a bump with the right-hand side shaded is this one. Are you comfortable that that picture and that are essentially the same? Now here's our next one. Oh, interesting. Do you see that it's greater than 27 and negative 2.4? So over here again, 27, well, 1 away gives you 26. It's still greater than, but it's to be greater than negative 2.4. And when I go down here, that is my p-value. Would you agree that guy is not very good evidence? Would you agree if I got a p-value of that, I would be saying, you ain't got evidence that is bigger than this fella? On the other hand, would you agree that this is pretty good evidence? Isn't that a nice small p-value? Scrolling. Suppose a study is done to test that the null hypothesis is 100 and the random sample of 56 gave me this fella and that guy. Now it says, what is the null standard error? Well, the standard error is S divided by the square root of n. N happens to be what in this story? 56. So I'm going to take 14 and divide it by the square root of 56. And that gives me about 1.87. I should check the accuracy. So 3 decimal places. So 1871 if you round it off. And that number there goes here. Now, this guy here is the sample statistic. So won't that be 103 take away 100 divided by that guy? So that's 3 divided by 1.871, and this time I get 1.6. What kind of accuracy did they want? So 1.603. Now I did both those calculations by essentially doing them by hand. And I could eventually use p-value and sort, but let's do it differently. Right, let's keep those numbers there and see if we can get all the answers by just using sort. Wow, I wasn't expecting that. Right, so if you click inferential statistics and one sample t, the sample mean in this story was 103. The sample standard deviation was 14. And the sample size was 50 something, let's check again, 56. Did you see that I didn't need to do degrees of freedom or anything? Didn't I just type in the information that they gave me? Now, it's a hypothesis test. In this particular story, don't we want the thing, well, that's 100, but aren't we trying to prove it's greater than 100? So this number is 100, and we are trying to prove that it's greater than. So that is basically us trying to do the null and alternate. Now, when I do generate results, equal to 100, greater than 100. Now, if we look at the standard error, can you see that 1.871? See it matches. If you go to the t statistic, can you see it's that number there? Right, now I need to get a p-value, so hopefully if I scroll, there's the p-value. So can you see that you don't need to do it by hand if they tell you enough information? What I could have said is they want that one too anyway. 4 decimal places, 573. Now, is this guy less than 0.05? No. And when it's a no like that, wouldn't you be able to have as your conclusion, not enough evidence to reject H naught? Right. Let's see what this story is talking about then. If the p-value cannot be, well, it can be found. So I don't need to do any more because that's all they wanted.